Good morning, good day, everyone. My name is Alexander. I'm a researcher at the FKI. It's German Research Center for Artificial Intelligence, and today with my colleague Katarina, we will introduce you to our pilot, to our demonstrator that we are developing in scope of HumAIne projects. And basically, the main topic of our presentation is smart or intelligent scheduling and how we can use it in our smart manufacturing pilot. So let's get started. Let me first introduce our organization quickly. This is one of the research departments of the German Research Center for Artificial Intelligence. Innovative factory systems, other known as smart factory, and our topics cover basically all the Industry 4.0 Landschaft. I don't know the audience here, are you from manufacturing or not, but basically this is, in other words, smart manufacturing or next generation factory automation. The vision is that by converging IT technology and operational technology that we have in the factory, we can enable digital factory that monitors, adapts, and then continuously improves itself. And here, here are 5 steps Here are 5 steps that we see in vision can enable us to reach the digital twin-driven manufacturing or autonomous manufacturing. We start with a very important, with a digital foundation where we create databases and very important interoperable interfaces. Then we enrich our data, increase quality of our data, and that enables us to make fine-tuning and to generate added value from our data. Here comes different algorithms, AI, data-driven, and also scheduling that will come later. That enables us to give our machines some intelligence, a lot of intelligence, where our machines now provides autonomously some skills that can be chosen and reconfigure in our production, and at the end it enables us or our machines to collaborate with each other in real time through these standardized interfaces. And the vision is that we then reach this digital twin-driven autonomous manufacturing. But now, what role actually the scheduling is playing here? Why scheduling is so critical, and why intelligent scheduling is so critical? So it enables us to go from periodic batch optimization that we have to real-time predictive reactive coordination in the shared production or manufacturing as a service use cases. It enables us cross enterprise resource allocation with confidentiality constraints, and also must have in today factories multi-objective trades-off optimization, for example, max span versus cost, energy, and quality. What challenges we have? First of all, real-time disruptions. We have breakdowns, we have urgent orders, and we must immediately react. We must immediately reschedule. Then we have dynamic uncertainty, unforeseen events, stochastic parameters. That's one of the biggest challenge. Of course, scalability, the complexity of the algorithms is and the problems is enormous. We have here computational interactability. Then we have confidentiality. For example, again, in manufacturing as a service, we need to preserve privacy constraints, and also as our manufacturing systems are reconfigurable now, configuration becomes also decision variable, so we must also take it into account. Going further. Yes. No. Yes. Let me now very quickly introduce you to foundational problems that we face here. Again, I don't know the audience, but let me just introduce. We have here two problems. First, classical one, job shop scheduling problem, where we have a set of jobs. Each consists of some operations with the precedence constraints, and then we have machines, set of machines on the floor. On each machine, we can execute one operation. And now the task is then to find the schedule which minimizes our make span or some other objective, so that we preserve this precedence of the operations and also the capacity of the machines. So we need to choose when and which operation comes or being executed on the machine. And even this problem proved to be NP hard already for machines more than 3. But then if we want to be more flexible, let's say we now say that one operation can be executed on more than one machine on set of eligible machines, we have now flexible job shop scheduling problem. And this is even more hard because it has two coupled sub problems. We have routing problem where we need to choose the machine where operation will be executed, and then we have scheduling problem. The takeaway from this slide will be that first we need the flexibility, but flexibility brings more complex and brings more conflicts, brings more complexity, and here it motivates us to use AI-driven approaches. Now to AI-driven approaches. So of course they are now dominating the field of also scheduling. What I want to show on this slide that we have different AI-driven architectures, and all of them can be combined through digital twin, modern digital twin infrastructure, and in that case contribute, mitigate their disadvantages and bring and enhance their advantages. For example, we have deep reinforcement learning. This is one of the most now widely used approaches. It enables us to learn end-to-end scheduling policy. It enables us to have milliseconds dispatch intervals, so we can dispatch the scheduling policy. And mostly it's being used now on machine level. Now we have also multi-agent systems, which are very good for distributed setups. For example, shared production or manufacturing as a service, where you have different factories that interact with each other. Here we have auctions, here we have classical holonic architectures, and then we have swarm intelligence or meta heuristics. Here we have, for example, genetic algorithms, we have ants colony optimization. These methods are natively multi-objective, so we can optimize, again, for example, make span versus energy and so on. And they're best for offline quality. We can optimize it in offline, and here we need more time, for example, more than 10 minutes and so on. Again, take away. By using modern digital tools, we can combine them, and that's what we are doing in our demonstrator. But I will show next slides. Now, jumping. Yeah. So before I introduce our demonstrator and architecture, let me quickly introduce you to 3 user stories that we are developing in scope of HumAIne project. I'll just spell them here. First, as a production manager, I want to create a schedule to optimize the production that for required objective while preserving security of the factory data. So preserving security of the factory data, again, very important in shared production use case, when we want to collaborate with other factories. But of course, we don't want to share our private data. The second user story, as a production manager, I want to dynamically prioritize the optimization objective, to adapt factory to different demands, and to decrease the energy cost or increase the production throughput. Here is directly we need multi-objective scheduling. That's also the focus of our use case. And the third one, as a production manager, I want to have clear overview of the system's performance metrics and metrics to update the weights of the scheduling algorithm if required. Here, the focus is on transparency of our algorithms. Yeah, that's closely connected with the with how our AI-driven algorithms are working, kind of black box things, and of course, to be using it in manufacturing, we want actually to understand what is going on in internally. Now let's come to our demonstrator. From now on, it starts a bit more technical and a bit more specific to manufacturing. We are using multi-agent systems to control our demonstrator because it's very modular and it simulates the real modular reconfigurable production. I also will be talking about holons for those who are not in the manufacturing and multi-agent systems. Just think of them as also special agents with some special qualities. For example, they are hierarchically self-similar, let's say, but you can just think about them as agents. So you see here we have our demonstrator. We have different production modules that can be coupled to the transport system in the middle, and we have various agents that control our hardware. Now, our architecture, first of all, is product driven. That means that our products that we produce, they, let's say, produce themselves. And here the main two agents or main two holons that controls it is one, the product holon or product agent in the middle that takes the information about the product and then runs through the production, interacts with the resource holons or agents, and then kind of produce itself. And then we have resource holons or agents. They are controlling our machines at the right-hand side. And yeah, basically through the interaction, they then produce the product. We have also service holon, but it's not important for us now. It's more for providing or introducing our factory to the shared production network. Now, yeah, as I said, our production is product driven, product digital twin driven. So we producing here in our demonstrator this, let's say, truck. It gives us some variability to play with, and you see here hierarchy of sub products, how we can produce it. Now each now each product and each sub product has its own digital twin. We use administration shells for these. Again, sorry for those who are not in the domain. These as administration shells, they are standard digital twins as we use it. Shortly, they describe everything and provides all the information that we need to produce this product. Not we, but the agent. You see that on the right side, when we want to produce a product, we spawn, let's say, the agent starting with the very top of the hierarchy. It gets this digital twin from the product, let's say truck, and now it knows everything what it needs to produce it. It also knows that this truck consists of semi-truck, for example, and semi-trailer. And knowing this, it also spawns its sub-agents, which also takes the description of these sub-products, and also they now know how to produce themselves. And we do this recursively down. Just a sec. Yeah, so we do this recursively, and this now we have some kind of hierarchy of sub agents that the goal of which now produce the whole product, and the production comes from the bottom to to top. Now we can have here two possibilities. We can go either production plan based or process plan based. Production plan based meaning that we already done some offline scheduling optimization, and now each sub product knows how to produce itself. We just need to recursively product the product, assemble the product. But here in our scenario now, we need dynamics online scheduling. That means that we use this process chain based production, meaning that each sub product, it knows just the sequence of, let's say, operations as I described in the flexible job shop scheduling problem. So each, for example, cab chassis here knows just high-level operations, how to assemble it, and then we need to find the machines online how to do this actually. Now, how we do this? Again, some specific model for those who are from Industry 4.0 and capability-driven manufacturing domain. We use here capability skill service model. For those who not, just shortly, by using this model, we know the machine, which production capabilities each machine can provide in our production. We also know which processes or also capabilities our product requires in order to produce it. And by knowing this, we can now match them using algorithms and find exactly the eligible set of machines for our scheduling problem. So we find the machines which can provide, which can produce our product. Now, knowing this, this can be, let's say, shown like this. For example, we have the product. It describes, it has this process chain information, and then let's say for the required capability 1 or the operation, we know that machine 1 and 3 can now produce this. Or for capability 2, we know that machine 2 and 3 can do this. And as soon as we know it, we can now use reinforcement learning to scheduling or choose the machine. And this what in the next slides, Katerina will tell you in more details how we use it. My last slide will be actually how we take everything that I describe you and how we combine this in the architecture that we use in our demonstrator in HumAIne. Remember the slide about AI-driven architectures that can be combined through digital twin infrastructure. This is exactly what we are doing here. We have standard digital twin infrastructure where we have these admin shells of each asset. We can describe robots, machines, also agent themselves. In the very bottom, we have our HumAIne platform. There we have Swarm deep learning scheduling algorithm running there. And in the middle, we have our multi-agent runtime that controls our manufacturing. We have our product hold-on, which is basically here scheduling agent, and then we have our resource hold-ons or agent. They represent each machine and then they control each machine. When we choose, when we have an operation, we choose first eligible machines that can do it, for example, machine 1 and 2. And they, in the background, ask our reinforcement learning services in the HumAIne generate the bid for us, and then we take part in the auction that taken place in the multi-agent system. And in that case, in that sense, we choosing the optimal machine that can produce this exactly step in this round. And that's how we produce our product. Right. That I think was it from my side. And now I give the floor to Katarina, who will describe and tell you something more about exactly the deep reinforcement learning scheduling algorithm.
Yes, so let's dive a little bit deeper into the scheduling algorithm and also in the multi-objective scheduling algorithm. So as Alexander already said, the underlying problem is the flexible job scheduling problem. So on the one hand side, we have our machines belonging to different companies, and even through in our test bed, like all the machines are located in one area, since they can belong to different companies, it's basically a shared production. And then we also have the task which must be processed. And for simplification, we use a sequence of tasks here. And then we want to create the schedule telling us which machine should produce which task at what point in time. And this problem is complicated by then the dynamic events, which can be machine failure or arrival of new customer orders or task failures, but also like the multi-objective optimization. So we want to dynamically prioritize the objectives and change them. And what our algorithm now does is basically that we loop through all the tasks which can be currently processed, and then the machines are issuing bits for each of these tasks. And the task is then assigned to the machine with the highest bit. And this is basically done as the production goes on and during processing. So we have in this way an online scheduling algorithm and incorporate like these new certain changes which are not known prior to the production. The interesting part now is here, how do we compute the bit? And for the computation of the bit, we are using reinforcement learning or multi-agent reinforcement learning. So each machine basically collects an observation vector, and it includes information about the machine and also about the tasks. So it's the processing time, there can be setup times, transportation times, but also the deadline of the job, or if we optimize for the energy, we also need the energy consumption, how much energy does it cost for the machine to produce this task. And this observation vector is basically the input to our machine learning model. And as output, we receive our bit, which is scaled between 0 and 1. And this is our reinforcement learning action. The bit is then taking part in the auction, and the machine with the highest bit gets the task assigned. So much to the single objective optimization algorithm. If we now have multiple objectives, then what we are doing is basically we have several machine learning models, basically one machine learning model for each objective. And then the machines are still collecting their observation vector. This vector is the input to all of our machine learning models. And then we receive one bit for each optimization objective. And we will combine these bits using any kind of utility function you want. The most common one is basically the weighted sum. So you combine all these bits, and the combined bit is then taking part in the auction process. In this way, we can change these weights dynamically because they are independent of the reinforcement learning algorithm. So they are independent of the machine learning models, which facilitates us to change these weights without retraining the model. So we have conducted some experiments for this. Here the experiments, or in this experiment, we optimize for the energy consumption and also for the lateness. And it's basically so constructed that the machines either can process a task very fast, but with high energy costs, or very slowly, but with few energy costs. And we want to make sure that the deadlines are adhered of the product but within this limit or range, we want to reduce the energy as much as possible. So that's also why we chose 0.9 for the lateness weight and 0.1 for the energy weight. And then we combined like 3 dispatching rules, one optimizing for energy, then minimal slack, which optimizes basically the lateness, 0, which is just a random order, and 2 reinforcement learning approaches. Some bits, this is basically the one I just introduced to you, and then reinforcement learning using some tree words, which is kind of the state of the art. In some tree word, we will apply the utility function inside the reward. This has the downside then if the weights change, we would also need to retrain the model. So on this fixed set of weights, we can do this and combine our outcomes, but not like for changing weights. So let's look at the results. So you can see that the reinforcement learning algorithms, they perform very similarly. You can also see it very good in the reward. So yeah, their performance is very similar, and then overall they are performing the best, so they achieve the highest reward. It's the closest to 1. Yes, so we can summarize that the performance is comparable to the state of the art, but the benefit of it is that we can explore the whole Pareto front. So in these plots here, I actually try to explore the Pareto front. So we can change our weights from 0 energy to lateness 1, to energy 1 and lateness 0 with just training 2 models, one for the energy objective and one for the lateness objective. And then basically compute all of the outcomes. Yes, so in summary, the whole benefit of it is that we can dynamically change our objective weights. We achieve equal performance. The downside is that we need a little bit more disk space because we have to store several of the objective or several of the machine learning models. But if the preferences are unknown in the beginning, or if they change very often, then basically our initial expenses by training several of the models in the beginning is outweighed in the long run, because we don't have to reach, or we do not need to retrain any of the models during production. Yes. So with this algorithm, basically we can conquer one of our user stories, which looks at the multi-objective or dynamic multi-objective optimization. Then there was another one looking at the confidentiality of the data between the companies. And for this one, we will apply swarm learning on top of this multi-objective optimist or scheduling algorithm. Basically on top of the multi-agent reinforcement learning algorithm. So what's basically going on is the machine collect the observation vector and issue the bit. The observation vector together with the bit is basically the data from which the machine learning model is trained. And this data is stored locally at the or with the machines. And then they will train different models, so distinct models from this local data. To now achieve one global model, the weights are exchanged and aggregated and then back propagated to the machine. So we receive one global model in total. In this way, we can ensure the privacy because not the raw data is exchanged, but only the model weights. We can foster scalability because we receive one global model, which actually helps us with the convergence to an optimal value. And we can increase also the generalization to different settings. So if now a new machine joins the network, you can distribute this global model to the new machine, and then it can issue bits and take part in the auction process. There are 2 alternatives from the state of the art. So one would be either to only use distributed training, then we could achieve like the privacy of the data. but we get troubles with the scalability and cannot generalize to new settings because you have different machine learning models for each machine. The other option would be to use centralized learning, which means every machine, they would share their data and train from the shared data, but then we cannot achieve the privacy, which we are looking for. So that's why we did go with this swarm learning approach in our case. And then let's look a little bit more into the implementation, how we did implement it in the HumAIne project. So on the right-hand side, you have basically everything which is locally done. So we have our production control, the auction process, the machines, and then to the machines are the reinforcement learning service connected. So this can be done at the companies. And then we have one global component, which is a swarm learning component. So we have one swarm learning server and then a swarm learning client for each reinforcement learning service. And inside this project, we basically implemented this and deployed this on Kubeflow. So Kubeflow is basically an open source platform to build, train, deploy, and manage machine learning workflows on Kubernetes. So one benefit from it is that it is cloud-based on Kubernetes, so we can scale it. And then it also helps us with the machine learning development and lifecycle. It has different components. We basically only use the Kubeflow notebooks for the model development and training. But you can also develop even more, like using Kubeflow pipelines. You can have machine learning workflows and orchestrate them. Or with K-Serve, you can also, serve different kind of models. Yes, for us, it has like the benefit that we can have this swarm learning component globally and deploy it on a HumAIne platform. So again, let's look how the process here goes. We have two concurrent processes, one the scheduling part and then the swarm learning part. The scheduling part is basically everything in black on the top, and then the swarm learning part concurrent to this is in green on the bottom. So starting at the factory control, if a new task comes in, the factory control is requesting from each machine a bit. The machines collecting their observations, they request a bit from the reinforcement learning services. So if two machines belong to the same company, they can also be connected to the same service component. Yes, the services are computing the bit and propagating it to the factory control. The factory control then sends the collected bits to the auction, and the assignment basically is returned, so telling us which machine then gets the task assigned. Concurrent to this, so in specific time intervals, the reinforcement learning services are issuing or sending their weights, their current weights, to the swarm learning clients, or to one swarm learning client, so either A or B. Then the weights are aggregated on one of the clients and sent back to the reinforcement learning services. And they are updating their machine learning models. So in this way, we can we receive a global model. We can share the information without sharing the actual data. Yes, and then that's basically how we can facilitate the second user story. Then that leaves us with the third user story, where we want to make the scheduling algorithm more transparent because we have different decision steps. So on the one hand side, we have our reinforcement learning services issuing a bit. This is a decision. And then we have our auction component, which also computes or evaluates which is the highest bid. This is again a decision. And then we also have the decision by the production manager about the optimization objectives. So basically multiple decisions which influence the total outcome of the schedule. And we want to or make it more transparent by visualizing the different steps. And for this one, Immersive Life, one partner of in our project, invented a user interface for the algorithm. So we have on the one hand side the machine view, the machine panels, where we have like some metrics about the machine, but also on the bottom here, the bits. So telling us like which task of the for which task the machine issued which bit, how high it was or how low it was. And then we have one central dashboard where we again have some metrics about the production, but also where the production manager can choose the weights of the optimization objectives and change them. There's a short demo video where you can see it and where it's demonstrated.
The AI augmented interface blends real-time data with virtual information overlaid in the physical world. In a one-time setup, the operator places virtual panels near the physical machines. Once set up, the operator gains access to a dashboard featuring several panels. The timeline panel displays both real-time and historical data, making it easier to track the manufacturing process. The performance panel highlights key factory metrics, helping the operator quickly assess performance. The objectives panel shows current scheduling objectives with an adjustable slider for easy fine-tuning. The machine view appears by each machine, displaying key metrics and the latest bits, providing the operator with instant context. With this interface, operators can easily interpret complex data, boosting transparency in production and improving decision-making.
Okay. So far, basically, 3 user stories and how we conquer them. We are not finished yet. The project is still ongoing, so we will most of the time evaluate what we have done so far. So we will conduct a user story for the HMI and also explore a little bit more the performance of the scheduling algorithm, especially in combination with the swarm learning technology. But still, there's some more, or there's future work which can be done, which we won't have time to explore within the project. For example, if you look at the last user story, we make the decisions transparent, but we don't really explain them. I think what would also be really interesting if we could explain especially the reinforcement learning decision, maybe using Lime or Sharp. So if we can track down how much influence one specific observation feature has on the end result, so on our bit, then this would also increase the transparency and explainability of the reinforcement learning algorithm. On the one hand side, we use also swarm learning to preserve the privacy of the data, but also with swarm learning, there are new attack vectors which come into play. Even though we are not sending the raw data between our machines or between our companies, we send like the model weights, and from the weights, sometimes you can also infer information. So one has to investigate whether it is possible in our case to infer this information, or whether this information you can infer is actually relevant for the attackers. Also, we only investigate our performance in benign settings. If there would be like malicious companies participating in the scheduling algorithm, then basically also the performance would degrade, and it would be kind of good to know like how much. Also investigating the fairness of the algorithm, we have not done yet. It would be interesting to know whether one of the companies might be favored before another. Yes, so before it should go into production, one has to consider this. But even though currently we are looking only at the scheduling problem, but you could actually transfer a lot of the approaches which we used to different optimization problems, because they show similarities. Like on the one hand side, you have the dynamicity, or you can also have the distributed setup with our machines in the different companies. For example, in the vehicle routing problem, so everything, or what's now in our case, the machine could then be the vehicles, and then you can transfer the reinforcement learning approaches, or you can also call them design patterns, to the different problem settings. So it's not everything what we researched about is about scheduling. We showed everything for the scheduling problem, but a lot of the approaches are also applicable to different problems. With this, we are at the end, and I give back to Brian.
Great. Well, thank you very much, both Alexander and Katarina, for the wonderful presentation and the overview of what HumAIne is doing in the smart manufacturing sector. I think the overall context, as well as the additional points that you've made in your continued conversation and the demo video as well, really helps to understand what is going on here.